So, while we're talking about the whole concept of improving resolution and making your chromatogram a little bit better, we have another concept that we can talk about in chromatography, and this is called the Van Deemter equation. Deemter, Van Deemter. And we're not going to do a lot with the equation, but I just need to present it to you so that way you've got a concept or a grasp about what the Van Deemter equation is actually all about. And we're going to talk about the variables that are inside of this equation and what they represent. But as far as actually plugging numbers in and actually calculating values and that type of thing, we're not going to do because that's out of our pay grade. So why do we want to worry about it? So the Van Deemter equation looks like this. HETP is equal to ABC. A, B, and C. However, the B is divided by a U, and the C is multiplied by a U. All right? So we've got to talk about what each one of these variables represent. Why are they there? Why are they important? What do they represent? And the very first one that I will talk about is the U. And the U is basically the velocity or the speed of the mobile phase. Okay? So whatever this B variable is, it looks like it's in reference to velocity of the mobile phase. And whatever the C variable is, it looks like it's also in relationship to the speed of the mobile phase. So basically the flow rate here is going to be very important. And the flow rate is represented by the U. That's really what velocity is all about, right? Okay, so let's talk about the A variable. The A variable is the very first one that shows up, so let's talk about it first. And this is going to be called Eddy Diffusion. So we need to talk about what eddy diffusion means. Well, this is something that we've kind of talked about already. It's basically the solvent takes different flow paths through the stationary phase. Right? That's what eddy diffusion's all about. We've actually talked about eddy diffusion already. We just didn't label it as eddy diffusion or title it as eddy diffusion at that time. We just said there's multiple flow paths involved. So basically in a column, if this is filled with stationary phase and a molecule comes into the picture, whether it's a solvent or whether it's a component of a sample, it doesn't really matter. Eddy diffusion takes place in both. That basically states that that particular particle can go straight through the column and out the other end, or it can kind of take its time and take the scenic route and go through the column and out the other end. And there's so many different number of choices that that molecule can undergo as far as paths or roads that it can take to get to its destination. Again, think of it as the interstate or think of it as the back roads. Which one do you want to do for that particular day? Some of us like one route over another, and molecules are the same way, and we call that eddy diffusion. Different paths through the stationary phase, and they do this at random, right? We've got no control over that. As far as B goes, what is the B variable? This is called longitudinal diffusion. All right, so longitudinal diffusion basically means that the concentrations are going to be different. The concentrations in the center are going to be the most, right? And you get lower concentrations as you go on the edges of the column. So the concentration of the analyte is less at the edges of the band than in the center. And there's no control or nothing that you can do over this either, right? And the problem with this is that B has a flow rate assigned to it. Well, that basically means that the flow rate's going to be different depending on what point of reference we're talking about. So again, if I've got a column and I've got this molecule, most of my molecule or sample will go through the center of the column. That's just what it does. However, every now and then, a molecule will be pushed up against the sides of the column as it goes through the column and travels down the stationary phase. The problem is that these outsiders, the ones that are touching the edges of the column, they travel a little bit slower. And that's why the velocity is listed with the b variable, because the center travels at a different speed than the edges of the particles do, right? And that's because friction is slowing them down. And that takes time. So therefore, time is going to change depending on what point of reference we're talking about as far as longitudinal diffusion goes. Okay, so finally we get the C variable, and the C variable is called resistance to mass transfer. And it's basically the time that it takes for the molecule to go from the stationary phase to the mobile phase, right? So here we get a column, and we've got a stationary phase particle basically here, and then off of this particle we get our components in the sample, right? So our components will kind of lodge onto the stationary phase. They stay there for a little bit, and then they come off and they go into the mobile phase, and they travel through the mobile phase, and then they get stuck on another stationary phase particle, and they stay at that particle for a little bit, and then they get dislodged, and they travel through the column a little bit longer with the mobile phase, and then all of a sudden they get stuck to another stationary phase particle. And this whole concept will go back and forth the entire time, right? That's basically what goes on in the world of chromatography. And we call that mass transfer. So there's a time that equilibration happens. And that time is in reference to the stationary phase and the mobile phase. The velocity of the mobile phase is very high, right? So the mobile phase is getting pushed through the column, and that has a certain speed associated with it. So that's why we see the U show up with this variable as well, because we're talking about speeds when it concerns stationary phase and mobile phase. When it's on the stationary phase, the velocity, of course, is different because it's not really traveling anymore. So I see a change in speed, and therefore the U has to be tagged along with the resistance to mass transfer as well. Okay, the A part does not get a U, and the reason is because eddy diffusion just simply states that it flows different ways through the column. The speeds never get affected. We're simply talking about a different path. So imagine the interstate and the back roads having the same speed limit, because in chromatography, it kind of does. It doesn't matter if you're taking the long way or the quickest way as far as distance goes. You're traveling at the same speed. And that's why we never see U assigned to the A variable in the Van Denkter equation. So that's what these three variables represent. U is the velocity of the mobile phase. A is eddy diffusion, which just basically means there's different roads that you can take to get to the same place. B is longitudinal diffusion, which means that if you're on the outside and you're touching the edges of a column, you're going to travel at a slower speed. And then C is resistance to mass transfer, which basically is the concept that the solute or the analyte attaches to the stationary phase, stays there for a while, then goes into the mobile phase and travels at a different speed before it attaches to the next stationary phase particle, and then eventually it makes its way out. All right, so we need to talk about what all of this basically means as far as an equation goes. Well, the Van Deemter equation gets a graphical representation. And basically what this graph looks like is that down here on the x-axis, it seems like everything is associated with velocity or speed, right? So I'm going to put velocity here on the x-axis. And then all of this has everything to do with the column, the different flow paths through the column, right? The other variable of mass transfer going from stationary phase to mobile phase, but that's happening in the column, okay? And then the other variable about it actually going through and touching the edges of the column. So really what we're talking about here is plate height. We're talking about the innards of the column, which is the stationary phase, and that flip book is made up of a certain number of pages, and those are, of course, the plate height. How many pages is that cartoon made up of? So if we graph the Van Deemter equation, we would get something that looks like this. All right, it looks very similar to a parabola. And then here is maybe the minimum that we see. Right there's the minimum. So if you go up and down at the minimum of that parabola, so a little bit of calculus and a little bit of math involved, and if you go left and right, where that minimum is actually located, you'll get an area here where it crosses the y-axis, and you'll get an area here where it will cross the x-axis. Those values are very important because what this minimum does, this parabola, is that if it crosses the x-axis, wherever that number is at, that will give me an optimum value. And that optimum value is the optimum velocity or the flow rate that I should be using in my chromatography system. That's really what this kind of boils down to, right? So the Van Deemter equation takes all of these factors into play, and it basically provides me some insight on what the optimal flow rate is going to be for my method that I'm using. Should it be a half mil a minute? Should it be 0.75 mil a minute? Should it be 1 mil a minute? Should it be 5 mils a minute? Right? Those are the answers that or questions that we have to answer. And sometimes it takes longer to go through all of that in a laboratory than it is just to solve an equation with these variables that are located there in order to give me the optimal velocity of the flow rate. Now, the y variable, this is talking about plate height, right? And this is basically the minimal plate height that I can have. So the minimal plate height is basically the shortest plate height that I can have in the column. So this gives me an idea of the size of the column that I can use and maybe have it the best column for my particular method. Now, keep in mind that the lengths of the columns do not necessarily correspond to the plate heights, not every single time. So just keep that in mind, and we're going to simplify this a little bit, and we're just going to say the Van Deemter gives me optimal flow rates for my method, and it gives me optimal column information. And we're going to say the size of column. But keep in mind that it's more than just the length. There's a width involved in the column. It's the number of plates in the column. There's a whole number of factors that go into the column information. But for us, we'll keep it simple and we'll just say overall size of the column. But keep in mind, we're really referring to more than just that. So that's the Van Deemter. That's one of the reasons that we never really use the Van Deemter equation mathematically, because there is quite a bit of math involved, and you can kind of imagine that going into this equation and solving some kind of number. But the graph of a Van Deemter will look the same no matter what. If you notice with the Van Deemter equation and this parabola, as the velocity increases, as you go faster and faster flow rates, notice that the plate heights have to kind of become larger. The plate heights have to become bigger and bigger and bigger. And then before the minimum, notice the same thing. The velocity, as you slow it down, the plate heights have to become larger and larger and larger as we go in that direction. So this really by all means is a optimal value. The bottom of that parabola is what we want to look for. Okay? All right. So we're almost finished with chromatography now. We know the Van Deemter equation, and just a few more comments that I want to make on chromatography before we close this section and this module out. So first, I want to say that chromatography now has came quite a bit of ways away from the days of chalk in a glass column with plant pigmentation. Okay, we now have automated equipment or instrumentation that will do this for us. We now no longer really use glass columns anymore. We now have better material. We do not use chalk anymore. We have better material for that as well. And chromatography has become very commonplace in a laboratory. It's one of the most widely and most common forms of methods or procedures that you will see in any laboratory, no matter the background of the lab and the products that they test. One of the things that I will say is that you just need nano quantities anymore to inject onto a chromatography instrument. Nano quantities. So keep that in mind. Nano is 10 to the 9th, right? So if I have 1 liter and I take 1,000th of that, that is a milliliter, right? 1,000. If I take 1,000th of that, that then sends me into microliters. And if you've used our microliter pipettes in the laboratory and you measure out 1 microliter, you know that that's just basically fractions of a drop. You probably can't even see that volume with your own eyes. And then if you take 1,000th of that, we're now into the nano quantities, the nanoliter volumes. So really fractions of a fraction of a drop is what we're talking about. And chromatography can pick those components up. It can see those analytes, and it can report those very well with very minimal problems. So very powerful pieces of equipment that we're going to be talking about this entire semester as far as chromatography goes. Next is that they're very reproducible, which means that I can get you and I can get someone from a different class to do the same lab and prepare the same samples and put those samples onto the machine, and I should not have any problems at all with the data coming out very, very close to each other, as long as you've done your job the right way. So it makes our life much easier in a laboratory. It looks at very small quantities. It can measure those quantities very systematically and over and over and over for me, so I don't really have to worry about reproducibility here. And then finally, like I said before, it is one of the most heavily used pieces of equipment in today's lab. So this is something that I will always see going on in a laboratory, no matter what background. And it's very important that you walk away from the class being very comfortable with running a chromatograph and knowing what chromatography is all about. The last word, again, you might have heard me say this before, on Merck Pharmaceutical is that they have had 1 HPLC unit for every person that they've hired that needs to use it. So imagine they've bought you your own HPLC system, because you will need to use that HPLC system when you're on your shift almost every single time. So let that sink in for a minute. There's hundreds of thousands of dollars that go in to chromatography instrumentation, and Merck Pharmaceuticals just one of them. If you go down to our pharmaceutical company in Wilmington, who's now called Alchemy, they will have 90 or more HPLC systems just in one room alone. Just one room. And they have sunk in anywhere between $50,000 to $80,000 per instrument because of the capability that they need. So tons of money gets wrapped up in this type of instrumentation. And again, we want you to feel very comfortable with working with the chromatography systems before you leave this class. All right, so that's it for Intro to Chromatography. As far as the instrumentation goes, well, this will turn off into another direction where we'll talk about pieces and parts, and we'll talk about the actual equipment itself a little bit later on. But as far as the general concept of chromatography now, I think that you've got it. So these are a few equations, a few terms that we will go through and talk about throughout the entire course. So you might as well use them now. We might as well introduce them now. So that way, when we do talk about them in reference to the equipment, you won't be lost. So if you've got any questions, you know how to find us. And until then, good luck with the assignments that come along with these videos.